Welcome, this is Professor Ridge. Today's lesson 4.3, Fitting Linear Models to Data. Our first learning objective, draw and interpret scatter diagrams. A scatter plot is a graph of plotted points that may show a relationship between two sets of data. If the relationship is from a linear model or a model that is nearly linear, the professor can draw conclusions using his knowledge of linear functions. So figure 1 shows a sample scatter plot. So on the y-axis here we have the final exam scores from 0 to 100. And then on the x-axis age. And you can see all these points. So this point right here would represent about 40 for the age and about a 60 on the exam. And notice that this scatter plot does not indicate a linear relationship. The points do not appear to follow a trend. In other words, there does not appear to be a relationship between age of the student and the score on the final exam. Okay, so it's kind of, the points are kind of scattered everywhere. It doesn't look like the younger the age, the lower score, the older the age, the higher score, right? It's kind of just all over the place. Example 1, using a scatter plot to investigate cricket chirps. So the table below shows the number of cricket chirps in 15 seconds for several different air temperatures in degrees Fahrenheit. Plot this data, determine whether data appears to be linearly related. Okay, so on the bottom, we're doing temperature. No, y is going to be temperature. So this is our temp in degrees Fahrenheit. Okay, and then degrees Fahrenheit, and then this will be 15-second intervals, or in 15 seconds. Okay, number of chirps in 15 seconds. Okay, so there's 44 chirps in 80 when it's 80.5, so 44 80.5 looks like right about just a little bit shade above. Okay, 35 70.5, 20.4, and 57. So right about there. So remember, if this is 50 and that's 60, 55's halfway, 56, 57, right there. 33, so 33 is about right here. 30, between 30 and 40, about a third of the way, 33, and then 66. So a little more than halfway. And look, it is, right, those 4 dots look like they're pretty close to a line. Not exactly, but we're saying, does it appear linearly? So far I'm going to say yes, but let's finish. 31 and 68. 31 and 68. 35 and 72. 35 and 72. 18.5, 52. 37, 37, and 73. Let me try that again. I think it's a little lower. I think this was supposed to be 1 dot. Okay, 37, 73, and then 26, 53. 26 and 53. Probably right about, actually, 26, a little more than halfway. Right about there. So you can see that kind of resembles a line. And there's an actual math way we can figure out what we call the best fit line, right? You can kind of, so let's just, I like these two and that one. Let's see if I can kind of hit. All right, so that would be a good model for this linear relationship. And then you can figure out that equation of that line, and then you can use it to predict about how many chirps per minute you would expect. So yes, it does appear linear. Example 2, finding a line of best fit. Find a linear function that fits the data in table 1 by eyeballing a line that seems to fit. So basically what I was just saying. So you can kind of eyeball it and say, all right, that looks like linear. Let me kind of move this line around. Let's see if it will still let me click it. Probably not. All right, and I kind of want to eyeball it. And I said, I want to go through this point and this point. So I can use those 2 points to come up with the equation of the line. So let's see, this one was 18.5, 52, and then let's do this one. That was the 3773.5, these two. So let's use these 2 points. Okay, so my slope will be, I'm going to do 0.1, 0.2, so 73 minus 73.5 minus 52 over 37 minus 18.5, which equals, okay, so the top's 21.5 and the bottom will be 37 minus 18.5, which is 18.5, and then 21.5 divided by 18.5 gives me a slope about 1.16. We'll round it to 2, about 1.2. Okay, so that would be my slope. So now my equation then is going to be, let's see, what function do you want to say? Number of chirps. Let's see, temp is the output, so that would be T. Chirps is going to be the input. So the mx plus m, well, it's C instead of x plus b. So we're going to put in the 1.2, and then we're going to put in one of these 2 points, doesn't matter which. We'll do the 18.5. And then the 52 for the output. So 1.2 times 18.5 equals 22.2. And then you're going to subtract that from both sides. So B equals 52 minus 22.2 is 29.8. So then we get T of C is M, which is 1.2, C plus 29.8. Now that's a little off from what even I drew here because remember I was 1.16 and I rounded 1.2, so that's going to be off a tiny bit from even what I eyeballed there. But anyway, now I can use this equation to predict how many chirps I'm going to get in a 15-second based on the temperature. So if the temperature is 90 degrees, 1.2 times 90. So if I said T of 90, okay, this is our answer here. T of 90 would be 1.2 of 90 plus 29.8. So we can roughly estimate that there will be plus 29.8. Roughly estimate there'll be about 138 chirps in a 15-second period if it's 90 degrees Fahrenheit. Recognizing interpolation or extrapolation. Okay, so while the data for most examples does not fall perfectly on the line, the equation is our best guess as to how the relationship will behave outside the values for which we have data. We use a process known as interpolation when we predict a value inside the domain and range. The process of extrapolation is used when we predict a value outside the domain and range of the data. Okay, so the different methods used to making predictions used to analyze data. All right, and that's basically what was set up here. All right. Example 3, understanding interpolation and extrapolation. Use the cricket data from Table 1 to answer the following. Would predicting the temperature when crickets are chirping 30 times in 15 seconds be interpolation or extrapolation? Make the prediction and discuss. Okay, so we're using, all right, I notice in the book they use some different numbers than I did, but they got 1.2 C plus 30, so we'll change this to 30 for our prediction. But we want to predict 30 times in 15 seconds. What's the temperature? So T of 30 and 1.2. Okay, so I'm going to use the book one just to kind of reset it. 1.2 C plus 30. So just basically you can round that one that I had. 1.2 times 30 plus 30. That would be 30. Is that 36? 1.2 times 30 is 36 plus 30 is 66 chirps in 15-second interval. Now, is that interpolation or extrapolation? So 1530, and if you look, 1530, do you see 1530? That's the domain of our data. The smallest one is this 18.5. So 15 is outside of what we have in our data set here, right? So it's below the smallest one. So that would be extrapolation. So that would be extrapolation. And then our prediction is going to be 66 chirps in the 15-second interval. And does that seem reasonable? Yeah, seems pretty reasonable to me. Okay, B, would predicting the number of chirps crickets will make at 40 degrees be interpolation or extrapolation? So 40, so again, we want to see, is it within the domain and range of the data that we have? And so 40, right? Well, 40. So yeah, that's well within our data set, right? Because our biggest one was 44 and our smallest one was 18.5. So 40 would definitely be within the data. So that would be interpolation. Make the prediction. So this one's interpolation. And then T of 40 would be 1.2 times 40 plus 30, which will equal 40 times 1.2 is 48 plus 30 is 78 chirps per minute, or in a 15-second interval. And does that seem reasonable? And again, yes. Typically, if it's interpolation, it's going to be reasonable. Extrapolation, you know, that it depends on how far away, how far outside the data. So typically with this best fit, interpolation is going to be really good, very reasonable. But if we were saying, well, it's going to happen at 120 degrees, maybe it's way off, right? Because maybe something happens. So interpolation, typically, it's going to be reasonable. Extrapolation, sometimes yes, sometimes no. The book has this nice figure just to kind of help you understand interpolation. So if here's the point 30, 70, and you can see that's within the data set. So that's interpolation. And then this point would be like 8, 40. And you see that's outside the data set. So that would be extrapolation. So hopefully that picture kind of makes it clear. Next learning objective, use a graphing utility to find the line of best fit. Finding the line of best fit using a graphing utility. While eyeballing a line works reasonably well, there are statistical techniques for fitting a line to data that minimizes the difference between the line and the data values. One such technique is called least squares regression and can be computed by many graphing calculators, spreadsheet software, statistical software, and many web-based calculators. You can do it by hand. It's a pain in the you-know-what, but you can do it by hand. Least square regression. But having said that, you don't want to do it by hand. You want to do it with technology. Least square regressions is one means to determine the line that best fits the data. And here we will refer to this method as linear regression. Okay. So on the final and the midterm, you can't use a graphing calculator, so you won't be able to do this. I may have a question on it in the quiz where you can use that. I'm going to show you on Desmos actually, so it's a little different. But if you had a TI 82 or 83, 84, 85, 89, any of the TI graphing calculators, you open up the lists. List 1, you're going to put in all the X values. List 2, all the Y values or the input output. And then you just click in a utility somewhere. There should be a menu that says something for statistics, and then look for linear regression. And then it'll ask you line 1, line 2, or L1, L2. Hit enter, and it gives you the equation. Okay, but I'm going to show you on Desmos. If you just search Google linear regression with Desmos, it should pop up, and it's kind of somebody created the technique already. So here it is. I'm going to put in the numbers from that table. So let's see here. All right, so we're going to put in X1. Let's see, 44, 35, so on. Okay, I'll type it all in and come back. Okay, so got it, everything entered, and then you can see here Y1, and they got about mx plus b, so m is going to be 1.14 and b is going to be 30. Okay, we don't need to worry about that. All right, so that's your equation. So m is 1.14 and b is 30. Pretty close to what I got originally. Remember, I did 1.16 and then I had 29.8. So it's all within, reasonable. Or eyeballing wasn't so bad. All right, so find the least square regression line. Where did my pen go? Okay, here it is. All right, so let me write that down. So that Desmos is great. Again, you have to probably, if you just search that, it's all programmed in there. Just do a Google search, linear regression Desmos. I think that's what I put in. You can also search on Google for linear regression using Excel, and I can show you how to use Excel. If you have a graphing calculator, you can do that. So anyway, So y is equal to, or if we're going to use it, t of c. M was 1.14, c plus b was 30.28. Okay, if we want to go to 2 decimal places. Distinguish between linear and nonlinear relations. Okay, that's our next learning objective. Distinguishing between linear and nonlinear models. As we saw above the cricket chirp model, some data exhibits strong linear trends, but other data, like the final exam scores plotted by age, are clearly nonlinear. Most calculators, computer softwares can provide us with the correlation coefficient, which is a measure of how closely the line fits the data. Many graphing calculators require the user to turn on diagnostics on selection to find the correlation coefficient, which mathematicians label as R. The correlation coefficient provides an easy way to get an idea of how close to a line the data falls. We should compute the correlation coefficient only for data that follows a linear pattern, or to determine the degree to which the data set is linear. If the data exhibits a nonlinear pattern, the correlation coefficient for a linear regression is meaningless. To get a sense for the relationship between the R and the graph of the data, Figure 7 shows some large data sets with their correlation coefficients. Remember, for all plots, the horizontal axis shows the input and the vertical axis shows the output. So look at this. Looks almost exactly like a line, so that's 1. This one, same thing, 1.8, and you see it's kind of spread around. 0.4, it's kind of more of a blob. 0, it's just all over the place. So basically, if you have 0, 0 is going to be nonlinear, right? Positive 1 line, that's a perfect line. This resembles a linear relationship, but it's 0.8, so it's going away. 0.4. Right, and then these are negative 0.4, negative 0.8, and negative 1. So the difference between 1 and negative 1 is, we say 1 is a strong positive correlation. So basically you're going to have a positive slope when you graph it, and this one will have a negative slope. Okay. All right. So basically, the closer to 1 it is, the more it resembles a line. So the example we did with the chirps, the R was 0.95, so that's a strong positive correlation. Right? So the closer you are to 1, the more it resembles a line. 1 or negative 1, right? Closer you are to 0, then it's not going to be a line. So again, we can sum that up with this table here. Correlation coefficient is value R between negative 1 and 1. If R is greater than 0, suggests a positive or increasing relationship. If it's less than 0, it suggests a negative or decreasing relationship. The closer the value is to 0, the more scattered the data. The closer to 1 or negative 1, the less scattered, right? So 1 and negative 1, it's resembling lines, and then closer to 0, it's just scattered all over. Okay, example 5, finding a correlation coefficient. Calculate the correlation coefficient for the cricket chirp data, and again on Desmos, it's listed right here, 0.9509. So 0.9509. So that suggests a strong positive linear relationship. Okay, our last learning objective, fit a regression line to a set of data and use the linear model to make predictions. Example 6, using a regression line to make predictions. Gasoline consumption in the United States has been steadily increasing. Consumption data from 1994 to 2004 is shown in Table 3. Determine whether the trend is linear, and if so, Find a model for the data. Use the model to predict the consumption in 2008. Okay, so we're going to plug this into Desmos. So let me do that. I'll be back. Okay, before I do that, we're going to make T, this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my input would be 0 and 113. Okay, so I put in all the points, and if you change the viewing window here for your X and Y axis, you can change it or zoom in, then you could see. Oops. All right, so then the regression will be M is 2.2 and B is 113.3, and you can see how those are kind of tightly, and R value is 0.99, so that's a strong positive or increasing relationship, and it resembles a line very well. Okay, use the model predict. Now we want to predict 2008. So let's see, our model was, so Y is equal to, M was 2.209, X plus B, which is 113, and so X is T, same thing, doesn't matter. So we want 2008. So 2008 minus 94, 2008 minus 1994, that would be what? 14. So we want to put in, so if we want to do consumption as a function of time, 2.209 T plus 113.318. Let's see, at 14. Punch that in your calculator to make your prediction. Oops, 18. All right, let me get my calculator out here. 2.209 times 14 plus 113.318. So that's going to be about 144.244. So that's our, so it's going to be about 144 billions of gallons of gasoline. Is this per year or what is it? Probably per year. Yeah, so it's the gallons for the year, right? And we're just making a prediction, you know. Well, now it wouldn't be a prediction. We can look it up, see how good that model worked. Anyway, okay, that brings us to the end of the lesson. So again, practice, practice, practice. So go to the end of the exercise set there and do as many as you can. Again, I just want to remind you on the midterm and the final, you won't be able to use a graphing calculator or Desmos. So I will probably not ask you any of these questions on the midterm and final. I may throw one into the on the quiz. Since the quiz, you can use those things, but just kind of keep that in mind. All right, have a good day, and I'll see you next time.